I was corresponding with one of my followers about the idea of detecting current in an AC line. And he was interested in, say, how to detect AC current in an AC line, and then especially related to the current that flows there, and say to get a kind of indication about that current, and furthermore not only an indication but say switching something with when that current in an AC line changes. And in the Netherlands we are talking about 230 volt at 50 Hertz. So this is the idea. Here we have the line voltage, 230 volt, 50 Hertz. Here we have, say, a measuring transformer, here, few windings. Then we have the load, here. It could be everything, could be a inductive load, or could be purely ohms load, like say a incandescent lamp. They are forbidden, by the way, in Europe. They take too much current anyway. Now we have LED lamps, but of course this can also be a LED lamp. It can also be a, say, heat element, and can also be, say, this and this are purely ohms resistances as a load. Here the load, purely ohms, but there can also be an inductor, say a motor. Well, of course when such a motor starts to run, in its first moment a certain electromagnetic field must be say realized to make that motor move. Say in general we have this situation. This is, by the way, the most extreme bare idea. Here we have that magnet, here we have that coil, and when we switch in, there is of course also a certain EMK, electromagnetic EMF, that's what I mean, force, back, etc. Don't want to dive too deep in this. Anyway, what are the things that you can encounter in such a circuit? At first, we have to do with 50 Hertz and 230 volts. That's AC. That means that such a coil, say, let's give it here a core, that the resistance of such a coil is frequency dependent. When you know a little bit about electronics, the AC resistance of coils, etc., you will surely know that. Anyway, there is of course here in that coil a certain relation between the windings here and the windings here. Say, that's important because we want to measure here quite high currents. This coil must consist of, say, a few windings, perhaps 10 windings, say 10 windings or 20 windings of very thick isolated copper wire, and here we have the secondary coil. So when current starts to flow, we get here a voltage drop, an AC voltage drop, we have induction, and then we have here a voltage out. And the relation between the number of windings here and the number of windings here is of course important. Say we have here 30 windings. And here we have, say, 5 windings. There is a relation between 5 and 30. When an AC current starts to flow here, through the load here, a current starts to flow, and that means that parallel to this winding there is an AC voltage generated, and that's inducted here. So not the amplification factor, but say the induction factor is, say, 6 times. You have to test that for your own situation. I've made this circuit, and I've used here the primary winding of this transformer. This is, by the way, a bad example because I've used a much more fierce transformer. But anyway, this is a standard, say, 230 volts to 6 volt or 12 volt transformer. And you can connect here on the low voltage side. Make these connections here. So a few windings, and that's here. Say this is the low voltage side, and here's the high voltage side. But of course, you know, when you use such a transformer, that there is an enormous, say, inductive effect related to the different windings, and that means that when you send in here, send in that current through that few windings winding, you get an enormous AC voltage out when, say, the load here starts to take AC current. It has also to do, say, with the properties of the core. I cannot get too much in detail. It's hobby. But when you study, say, the more serious electronics books, etc., there's a very important thing, and it is a saturation of the coil. Say, when the maximum current flows here, in this part, and the coil gets saturated, there is no longer, say, a relation between the current that flows here and the output voltage that we see here. So that's important. And such a current transformer can be made in many ways. I've made one of them in the past, and want to tell more about it. This is, of course, hobby. For serious things, go to the World Wide Web, say, electronics books, etc. Such a transformer is in fact, this transformer is in fact, has in fact, I have to take it out, take some time, has in fact the same properties as this transformer. This is a laminated core made of steel plates of very, very thin steel plates of specific steel. They are pushed together, and that means that such a transformer made for 50 Hertz has a certain saturation when the current through such a transformer gets too high. Anyway, when you want to use a coil for such a circuit that does not saturate so easily, you can use this. This is a ferrite ring core, and you can make, for instance, for such a transformer, say, then I mean current transformer, to pick up the maximum current or smaller currents on AC. You can, for instance, wind here 10 windings and here say 20 or 30 windings. Put that 10 windings here in the lead to the load, could be everything, and then take out the current, and take out the voltage, the AC voltage, and you out of that secondary, that's here, sorry, and then measure the AC voltage here, etc., etc. So this is a good idea to make a current transformer that can indicate, pick up a certain AC voltage when in the primary part of that transformer a current starts to flow. And because this material does not easily saturate, there could be a better linear response regarding the voltage that you measure. Say with ferrite you could have this response, and with such a transformer you could have, of course you must test that in the practical situation, of course, you could have this response. So say on a certain moment the saturation is so big that you cannot measure here any longer the different currents that are flowing here in the primary. Anyway, so that was more or less all to tell. I want to give a somewhat other demonstration. Here you will surely see that when you make this circuit you have here an AC voltage. So what can we do with an AC voltage? Well, that's completely logical. We can rectify it with a bridge rectifier. So here we have that bridge rectifier. Plus, min, positive, negative, and you can use here any bridge rectifier, but of course that rectifier must be able to rectify that voltage. When that voltage is high, you need a bridge rectifier that and of course also a capacitor that can handle that voltage. So say we have here a capacitor of 450 microfarad, only an idea. We have here say a voltage that an AC voltage that changes between say 3 volts AC and 20 volts AC, and we rectify it. We can see here, because that bridge rectifier gives out 1.4 times the AC voltage. Say we can see here voltages appear in the order of let's say 5 volt up to 30 volts. So again, only a hobby circuit. I don't know what will happen when you connect here not a ohms load but a inductive or capacitive load. Did not test it, only tested it in practice when I wanted to make an AC power supply and wanted to see the AC current, and that is this power supply, by the way. Inside this power supply here that I'm using always in all my experiments, and when you have followed my channel you will surely know that there is such a transformer, AC transformer. Anyway, thanks for watching. Well, you could do many experiments testing different transformers, study when such a transformer gets the core of the transformer gets saturated, make a table about the current and the voltage that is happening in the circuit. Try to use ferrite materials for such a current transformer, etc., etc. Thanks for watching.